Let us consider one more example. Let x of t be equals to 3 e power minus 4t ut minus 2 times e power minus 2t ut. Let's try to calculate the Laplace transform, that is x of s equals to integral from minus infinite to infinite x of t e power minus st dt. So that is going to be equals to integration from minus infinite to infinite x of t is 3 e power minus 4t ut minus 2 e power minus 2t ut times e power minus st dt, and now I will write it directly. It is going to be 3 integral 0 to infinite e power minus s plus 4t dt minus 2 integral 0 to infinite e power minus s plus 2t dt. And this from the previous and what we have seen so far, we can directly write this expression, that is going to be equals to 3 pi s plus 4 minus 2 pi s plus 2, or I can simply simplify this, and that is going to be equals to 3s plus 6 minus 2s plus 8 whole divided by s plus 4 times s plus 2, and that's what you will get the expression something to be x of s equals to s minus 2 divided by x of s is going to be s minus 2 divided by s plus 4 times s plus 2. And of course the region of convergence here, based from what we have seen before, this region of convergence for the first integral is going to be sigma greater than minus 4, and for the second integral it is going to be sigma greater than minus 2. So let me write that. So ROC is going to be sigma greater than minus 4 for the first integral and sigma greater than minus 2 for the second integral, and combinedly, as we know that we have to satisfy both of this integration, the convergence of both of these integrals, so we would stick to the condition which would satisfy both of these ROCs. So sigma greater than minus 2 and sigma greater than minus 4 gives you the condition as sigma greater than minus 2 as a common condition for the convergence for both of these integrations. So that is the region of convergence and the complete expression indicating the Laplace transform of the given signal. If I try to draw this region of convergence in the S-plane, it is going to be something like this. Let this be, say, minus 2. Let this point be minus 4. And of course this is 0. Axis being j omega. And this axis being sigma. Then the region of convergence, as we have seen here, is going to be sigma greater than -2, so it is going to be something like this. So everything greater than -2 comes in the region of convergence. So I'll draw that like this as a shaded region. So it is going to be like this. Everything that satisfies sigma greater than -2 is the region of convergence. So this is the region of convergence, that is ROC. Now let's make some observations with respect to this Laplace transform. Now as you may see that the expression that we have obtained, unlike what we have obtained previously, is having this s-2 in the numerator. As you may observe from the previous examples, here this example 2 and for this example 3, we were not having any s term in the numerator. So you can see from here. But now we have this s term in the numerator as well. In fact, the expression that we have obtained is going to be in a form of a rational expression. It is going to be a rational expression, meaning it is going to be a polynomial in the numerator as well as in the denominator. So in general, this x of s, or a Laplace transform, is going to be a rational function of s, meaning it is going to have a polynomial in s in the numerator divided by a polynomial in s in the denominator. So such kind of function is called as a rational function, where we have a ratio of two polynomials in s. Now as we have this ratio of polynomials, we may find their roots, and if we try to find the roots of the numerator, they are called as zeros. What I mean by that is, let's say if I equate the numerator polynomial to 0, what I will get is s equals to 2. And if I substitute this s as 2, you may see that 2 minus 2, it will get cancelled, and this x of s is going to be 0. Therefore, the value of s for which this expression turns out to be 0 is called as zeros. So let me indicate that this term here, when equated to 0, that means the roots of the numerator when equated to zeros is called as 0. They are called as zeros, and they are indicated by circles on the graph. So where do we have this 0? It is at s equals to 2. When this s minus 2 is equated to 0, we get s equals to 2. Therefore at s equals to 2, we do have 0 there. So where is s equals to 2? If this is s equals to 2, then we do have a 0 there. So 0 is indicated by a circle, so I'll indicate that with a circle like this. So this indicates that there is a 0 present there, or a root that makes this expression 0. Similarly, if we try to find the roots of the denominator polynomial, the roots of the denominator polynomial are called as poles. For example, if we try to find the roots of this denominator, you may see that these roots are going to be s equals to -4 and s equals to -2, because when s plus 4 is equated to 0, it gives s equals to -4, and when this s plus 2 is equated to 0, it will give s equals to -2. If I put either of these values in the denominator, let's say if s equals to -4, this expression shoots to infinite. Or if I substitute this s as -2, again this x of s shoots to infinite. Therefore, the value of s for which this expression shoots to infinite, it is called as pole. So these roots, or the polynomial roots of the denominator, are called as poles, and they are indicated on the graph as these crosses. So we do have a pole at s equals to -2, and we do have a pole at s equals to -4. So I'll indicate that with a cross at -2, and a cross at -4. Now we didn't mention any poles and zeros in the previous example, so let's do that. So for previous example, as you can see that here in this case, we got the expression as -2 upon s square minus 1. So there is no 0 present just because there is no polynomial in s in the numerator, but we do have a polynomial in the denominator. So the roots of this is s plus 1 and s minus 1. So there are two poles here. Just because this degree of this polynomial is 2, there are two roots that makes this x of s to infinite. So we do have a pole at s equals to -1 and a pole at s equals to +1. So I'll indicate it with crosses. So this is one pole and that is the another pole. Similarly, for the other examples, say for example the example on the right, we have this 1 upon s plus 1. So we have this one pole at s equals to -1. So I can indicate that as s equals to -1. I'll indicate that with a cross. So this indicates there is a presence of one pole at s equals to -1. Similarly, for the expression on the left, we do have a pole at s equals to -1. So what do you mean by pole? Pole is simply the value of s that makes this expression infinite. Similarly, a 0 is the value of s which makes this expression 0. So let me write that. So the expression or the terms that we have defined, let me write that. The first is the pole. Pole is simply, poles are the roots of numerator polynomial, the denominator polynomial of denominator polynomial and they are given by these crosses, they are indicated by these crosses, and zeros are the roots of numerator polynomial, and they are indicated by these circles. These poles makes or I will indicate that with the definition, the values of s that makes the function 0. Here, just because it is pole, it will make infinite. It is called as the pole. So the poles are those values of s that makes the function infinite. Similarly, zeros are those values of s, the values of s that makes the function, which function? The Laplace function, as 0. These are the definitions of poles and zeros. Let's talk